harder integration of trigonometric functions. So here we're going to look at a few examples on some harder integration of trigonometric functions. So the first one we're going to look at is the integral of sec x tan x dx. And the way we're going to solve this integral, we're going to make a substitution. We're going to let u equal to sec x, which means we can find du dx, and derivative of sec we don't actually know directly, so we're going to change sec x into 1 over cos x, and we can rewrite that as cos x all to the minus 1. Careful to not confuse it with the inverse function of cos. And here we can use the chain rule to derive this, so we can bring our power to the front, left with cos x minus 1 from the power to get minus 2, and times by the derivative of cos x, which is negative sine x, so we can tidy this up. So two negatives will cancel. We've got the sine x, and the cos x to the minus 2 we could write in the denominator as cos squared x. And just to make this a bit easier, we're actually going to rewrite this as sine x over cos x multiplied by 1 over cos x. Sine x over cos x is tan x, and 1 over cos is sec x, and this was equal to du dx. Now remember, we let u equal to sec x, so we can put that u back in here. So we'll get du dx equals u tan x, and we'll make dx the subject, and this will give us du over u tan x. And let's go ahead and make all these substitutions now. So we're going to get the integral of sec x, which we let equal u, times tan x, times dx, which we know is all of this. So let's go ahead and sub that in. So multiplied by du over u tan x. And what happens here is the u and the u will cancel, the tan x and the tan x will cancel. So we're just left with the integral of du. The integral of du is just going to be u plus our constant. And remember, we just got to put it back in terms of x, and u equaled sec x. So we're going to get the integral of sec x tan x is going to be equal to just sec x plus a constant. Alright, so another example. Let's look at the integral of sec x dx. So we know that the integral of sec squared x is tan x, but what's the integral of just sec x? Now, in order to do this, we need to do a bit of a trick here. And what we're going to do, we're actually going to multiply our sec x by a factor of 1. We're just going to choose something really special to help us out. And we're going to multiply by sec x plus tan x over sec x plus tan x, because we have to multiply by 1. So you can see that that over that would be 1, and we haven't changed the question. This is just going to work out nicely. So what's going to happen? Let's expand things out. So we're going to have the integral of sec times sec is sec squared x. Sec times tan is just sec x tan x over our denominator now, which is just sec x plus tan x. So why did we do that? Well, the derivative of tan x is sec squared, and we just saw that the integral of sec x times tan x was sec x, so that means the derivative of sec x is sec x times tan x. So what we have now is we actually have the derivative of the denominator is in the numerator. So we'll actually be able to solve this integral directly now, just saying it's the natural log, the natural log of the absolute value of the denominator. So we get the natural log of sec x tan x, all absolute valued, plus a constant. So if you ever get the integral of sec x, you need to remember this little trick here. Let's have a look at another question. So we're going to look at the integral of cosec x cot x dx. So it looks kind of similar to the integral of sec x times tan x. We've got two trig functions multiplied together. And similar to the other one, we are going to make a substitution. And if you get this, you want to let u equal to cosec x. So let's go ahead and muck around now. So we can say, we can find du dx. Might not know the derivative of cosec straight away, so we can rewrite it as 1 over sine x. And we can rewrite that as sine x to the minus 1. Now derivative, we can bring that power to the front. Minus 1 from the power, and times by the derivative of the inside, so we're using the chain rule. Derivative of sine x is just cos x. We can muck around with this a little bit, so we can say this is going to be minus cos x over, because we got sine x to the minus 2, so it's just going to be over sine squared x. We can rewrite this as minus cos x over sine x times 1 over sine x. Just breaking it up. It's going to help us see that minus cos over sine is going to be minus cot x, and 1 over sine x is cosec. And remember that we let u equal cosec x, so we can rewrite du dx as minus u cot x. We'll go ahead and make dx the subject, so we're just going to get dx equals minus du over u cot x, and we can go ahead and make our substitutions. So all this is going to equal cosec x is u, we'll leave our cot x, and dx we know is minus du over u cot x. And what's going to happen? The u and the u will cancel, cot x and cot x will cancel, so we're just left with the integral of minus du. This is just going to be minus u plus a constant, and remember we let u equal cosec x, so put it back in terms of x, so we're just going to get minus cosec x plus a constant as the integral of cosec x times cot x. Alright, another example. We're looking at the integral of cos x sine x dx. So it looks pretty straightforward. But in order to do this question, first let's have a look at a certain scenario. Let's have a look, what happens if you got the integral in the form of f dash x multiplied by f of x dx. So what happens if we have a product of two things inside an integral where one of them is the derivative of the other? What we can do, just to see what happens, we can let u equal to f of x, which means that du dx, just the derivative of f of x, which is going to be f dash of x, and making dx the subject, we'll get du over f dash x. And let's go ahead and sub it in. So we're going to get the integral of the f dash of x multiplied by f of x, which we let equal to u, times dx, which we know is du, over f dash of x. So the f dash of x's will cancel, and we're just left with the integral of u du. And this is really easy to solve now, because we know we're just going to get a half u squared plus a constant. And we could go ahead and sub in our u as f of x to get it back in terms of x. And we're going to do a similar approach with the integral of cos x and sine x. So the derivative of sine x is cos x, so we do have it in this form, where we have a product of two terms and one's the derivative of the other. So when you have that situation, you want to let u equal the original function, where you know the derivative of that function is the other one. Because we know that du dx is going to be cos x, and making dx the subject, we'll have du over cos x. So what we're going to have is we're going to have the integral of cos x times sine x, which we know is u, times dx, which we know is du, over cos x. The cos x's will cancel, and we just have the integral of u du. We know that's going to be a half u squared plus a constant, and we just go ahead and sub in our value of u, which we know u is equal to sine x, so we get a half of sine squared x plus a constant as our answer. Alright, let's have a look at another example. Let's look at the integral of cos to the 4x dx. Now, when dealing with trig functions with even powers, what you want to do is you want to use your double angle results. So let's make a note that we know that using our double angle results, we know that cos squared x is going to equal to a half outside of 1 plus cos 2x. But we have cos to the 4, which means we need to square both sides. So we're going to, because if we square cos squared, that's going to get us our cos to the 4. We need to square this side as well. So we're going to get cos to the 4 squared is going to equal to, well, we can square the half, which is going to give us a quarter. And let's just leave this as 1 plus cos 2x all squared. So we can go ahead and sub that into our integral. The quarter will go on the outside of the integral. So we're going to have a quarter times the integral of 1 plus cos 2x all squared dx. From here, we want to expand it out, because it's not too difficult to expand out a squared. So the integral, we'll square the first term, which is 1, plus double the product. So we're going to get 2 times cos 2x, plus our last term squared, so we're going to get cos squared 2x, all integrating with respect to x. Now, we've got this cos squared term in there, which we don't really want to integrate like it is now. So what we want to do is we actually want to come back to our original formula for cos squared x and our angle is 2x instead of x. So all we need to do is sub in 2x for x, and we'll get a nicer term to deal with. So subbing in, let's do it over here. So if we have cos squared of 2x, we're just subbing in 2x for x. So we're going to get a half outside of 1 plus cos of 2 times 2x. So that's just going to be a half outside of 1 plus cos 4x. And that's what we want to sub in for cos squared 2x. So we're going to get a quarter outside of 1 plus 2 cos 2x plus a half outside of 1 plus cos 4x, and all of this we need to integrate with respect to x. So let's go ahead and expand our brackets. So we've got the quarter integral of 1 plus 2 cos 2x plus a half plus a half cos 4x dx. And now we've turned this into something which we can integrate. We can integrate all of these terms. So we're going to get, you can tidy it up a little bit more by adding the 1 and the half, so we'll just do that. So we get a quarter times 1 plus a half is going to give us 3 on 2 plus 2 cos 2x plus a half cos 4x, all with respect to x. Now, all we need to do now is, because we have the addition of 3 terms here, we can just integrate all of these separately. So we're going to get a quarter times integral of 3 on 2 with respect to x is just 3 on 2x. Now, integrating cos is just going to give us sine, but we need to be dividing by the derivative of the function inside. So we have our 2x, so we need to be, derivative of 2x is 2, so we need to divide this whole term by 2, and it's going to give us sine of 2x. Same thing for this one here, so we're going to get the half times, we have to divide by the derivative of the term inside. The derivative of this is 4, so we need to divide by 4, or times by a quarter, and we're going to get sine of 4x. We're going to have to add on our constant as well. So it's going to come down here and tidy this all up. So let's expand. So we're going to get a quarter times 3 on 2 is going to be 3 on 8. So we're going to have 3 on 8x. The 2 on the 2, we'll just simplify to 1, and a quarter times the rest will be plus a quarter sine 2x. Then we've got a half times a quarter is an eighth, and an eighth times a quarter is a 32nd. We're going to have 1 on 32, sine of 4x, plus our constant for our final answer. So just remember, you have an even power on your trig function, you want to be using your double angle results. Alright, so another example. Let's look at the integral of sine cubed x. So we just spoke about even powers. What about odd powers? Odd powers we'll actually want to break up looking something like this. So we want to do the integral of sine x times sine squared x dx, because sine x times sine squared gets us back to sine cubed. And then we'll actually want to manipulate the sine squared x using just our normal trig identity of sine squared plus cos squared equals 1. So we should know that sine squared x equals 1 minus cos squared x. So we're going to go ahead and sub that in for sine squared. So if we do that, we're going to have the integral of sine x times 1 minus cos squared x dx, and we'll go ahead and expand this out. So the integral of sine x minus sine x cos squared x dx. Now, we've got two terms here that we're trying to integrate. We definitely know the integral of sine x, so we don't have to worry about this. So this is our next part that we need to worry about. So we might split this up into the integral of sine x dx minus the integral of sine x cos squared x dx. So we're just going to leave that integral of sine x for now. Now, for the integral of sine x cos squared x, whenever we have a product of trig functions, we can think about one being the derivative of the other, especially when they're sine and cos, because we know the derivative of sine is cos and the derivative of cos is minus sine. So looking at this one with the larger power is the one we want to treat as our substitution. So what we're going to do, we're going to let u equal to cos x. So we're going to get du dx equals minus sine x, make dx the subject. So we're going to get minus du over sine x. So let's go ahead and make that substitution. So we're going to get minus the integral of sine x. Now, cos x we let equal to u, so we're going to have times u squared. And dx we know is going to be minus du over sine x. The sine x's will cancel out. The negative here we can take outside the integral, and this will turn positive. So we get plus the integral of u squared du. And now we can go ahead and integrate this. So integral of sine x is minus cos x plus the integral of u squared is just going to be a third u cubed plus our overall constant. Technically we get a constant for this one, and adding those constants just gives an overall constant. Now we can go ahead and just put everything in terms of x, and remember u equaled cos x, so we're going to get minus cos x plus a third of cos cubed x plus a constant for our final answer of sine cubed x. All right, we're going to have a look at one more example. And this one's going to be the integral of sine cubed x times cos squared x dx. So this one's going to be a bit involved. And the first thing we want to do here is again use our trig identities to turn this cos squared x in terms of sine, because we'll be able to bring all the sines together and get something hopefully familiar. So we're going to end up with the integral of sine cubed x. Now we'll change cos squared into 1 minus sine squared. And we'll go ahead and expand. So we're going to get the integral of sine cubed x minus sine to the 5x dx. We just have a subtraction of two terms inside this integral, so we can rewrite this as the integral of sine cubed x dx minus the integral of sine to the 5x dx. We actually just did the integral of sine cubed x, so we're not going to go through that again, but now we need to tackle the sine to the 5x. And this might be a bit tricky. So just for the rest of this, we're just going to focus on the integral of sine to the 5x. Because we already know the integral of sine cubed x. Let's write it over here, just so we have it when we need it. So remember, the integral of sine cubed x ended up being minus cos x plus a third cos cubed x plus a constant. So we'll need that for later. Now, how do we do sine of the 5x? Well, again, similar approach. When it's an odd power, we want to write it as sine x times something with an even power. So sine to the 4x. And to do this, we know that sine squared x equals 1 minus cos squared x. And to get sine to the 4x, we just need to square both sides. So we're just going to square this side and square this side. That's going to give us sine to the 4x. Now we'll square the first term to get 1 minus double the product. So we're going to get 2 cos squared x plus squaring the last term is going to give us cos to the 4x. So let's go ahead and sub all of that in. So we're going to get the integral of sine x. Should be dx up there. Now sine of the 4 we know is 1 minus 2 cos squared x plus cos to the 4x dx. And let's expand all this. So we're going to get the integral of sine x minus 2 sine x cos squared x plus sine x cos to the 4x, all integrating with respect to x. Now we're summing up 3 terms here, so we can just take all these integrals separately. So we're going to go ahead and write them out. So we're going to have the integral of sine x dx minus 2. We can take the 2 outside this integral of sine x cos squared x dx plus the integral of sine x cos to the 4x dx. In order to do this a little easier, again, we have the situation where we have a product of sines and coses, which means that one of them is the derivative of the other. And the one with the bigger power is the one we want to let be the substitution. So in this case, our substitution is actually going to hold for both of these integrals. We only have to do one. So we're going to let u equal to cos x because it has a bigger power. So we're going to get du dx, derivative of cos is minus sine, and we'll make dx the subject, and we'll get minus du over sine x. We'll leave this integral of sine x for now, minus 2 times the integral of sine x. Now cos x we let equal to u, so we're going to have u squared times dx, which we know is minus du over sine x, plus, so we're using the same substitution for this one, of sine x. Cos x, remember, equals u, so we're going to get u to the 4, and dx equals minus du over sine x. So we can tidy this up a little bit. So the sine x's will cancel out in both integrals. This negative will cancel out this negative and become positive. And this negative will turn this positive into a negative. So what we're going to get, we're just going to get the integral of sine x, which is minus cos x, plus 2 times, we're just left with the integral of u squared du, so we're going to get times 1 on 3 u cubed. Now remember, this next one turned into a minus, and now we just have the integral of u to the 4 du, so we're going to get a fifth, u to the 5, plus our constant. And now we just need to sub in our u equals cos x to turn everything back in terms of x's. So we're going to get minus cos x plus 2 over 3 cos cubed x minus 1 over 5 cos to the 5x plus our constant. But remember, that was just the integral of sine of the 5x. We broke the problem down into the integral of sine cubed x minus sine to the 5x dx. So remember, sine cubed equals all this. So we're going to end up with this minus this as our final answer. So we're going to get minus cos x plus a third cos cubed x minus cos x plus 2/3 cos cubed x minus a fifth cos to the 5x. And we're just going to have our constant on the end. And what's going to happen here is that we're going to have minus cos x minus cos x, so it's going to be plus cos x, so they're going to cancel out. So these will cancel out. We have a third cos cubed x minus 2/3 cos cubed x is going to give us minus a third cos cubed x. And then we've got minus a fifth, which is going to be plus a fifth cos to the 5x plus our constant for the final answer of the integral.